Okay, so I was asked to provide an overview of cross-site request forgery, and also look at an example of SQL injection and kind of describe why it's vulnerable, why a piece of code might be vulnerable, and what someone might do to resolve that, or why it's an issue. So we'll start with cross-site request forgery first. In terms of what it is, it basically allows a malicious attacker to use a logged on session for some user to perform some action. So generally, web applications that have task-oriented URLs, whether it's transfer money, change a password, things like that, that execute some sort of task that's relevant to the user who's authenticated, cross-site request forgery can be used to basically hijack that session or ride that session and perform some sort of malicious act. A very simple example would be something like the user logs into his online banking site. When that happens, the browser and the application code for that website sets a cookie to track that user session and to authenticate the user session. The user's mail client maybe is configured to render HTML in emails. And then a malicious attacker might send an email with an embedded link or an embedded image or something like that that's got malicious code or a malicious request embedded in it. And so what happens is your mail client will then send that request or submit that request to the URL specified. And because you already have a cookie established for establishing your session and your identity and authenticating you, that cookie is sent along with the request, basically allowing whoever created that link or that embedded request to perform some action on your behalf without you even knowing. And the worst part is that it looks like it's coming from the user who's authenticated. And so it's a really big deal. I don't know of we'll talk about it in just a moment, but I don't know of any significant compromises other than a handful, but the potential is devastating, ostensibly, obviously. So as an example, suppose an HTTP request for your bank's online banking website allowing you to transfer money looks something like this. You'll notice that the cookie gets established or it relies on the cookie, and then there's three parameters involved in this post. So the amount you want to transfer, the routing number you're transferring to, and the account number. So if you're a nefarious actor or you're trying to compromise this particular account, you send some sort of email, or you get the user to browse to a website that's owned by you that has a form that you can submit. The form, if you look at the action, is the bank account, or I'm sorry, the online banking website. It's that transfer function. It's got the three form fields that the post is looking for in terms of processing the transaction or processing the transfer. And then it's got a button that says submit and win money. And because everybody likes to win money, if you click on submit, this request will get posted, and it will use the cookies, the session cookies that you've already got established because you're still currently authenticated into your bank's website. So you can see, like, it's a very sort of trivial thing to build something that will take advantage of cross-site request forgery. It requires some element of luck on the part of the attacker, but if you know how to sort of make this work for a given website or a banking institution or whatever, an application or a web application that's vulnerable to cross-site request forgery, then it's just a numbers game. So if you can submit, if you can spam 300,000 people and you only get hits from a handful of them, the odds are out there that somebody will be authenticated to their banking website when they click on your link or when they load your email in their HTML rendering mail client, or lots of other ways that this could potentially go down. So it's a very big issue. It's a very big risk. People who develop code need to consider mitigating this particular vulnerability. Cross-site request forgery in conjunction with cross-site scripting is particularly potent for an attacker if a web application is vulnerable to both, because some common mitigations for cross-site request forgery can be defeated using cross-site scripting vulnerabilities. And OWASP actually points to the MySpace Sammy worm, which was able to propagate itself, not really propagate itself, but be propagated because of not only a cross-site request forgery vulnerability, I guess with MySpace, but also with a cross-site scripting vulnerability that was able to defeat the one-time token usage that they had implemented. So I actually looked around and I didn't find any significant like large scale compromised issues thanks to cross site request forgery. TP link was the biggest thing I was able to find. And it looks like just reading up on this particular compromise that 300,000 routers or so that give or take were compromised using a known cross-site request forgery vulnerability. And what the attackers did is they reconfigured the DNS settings for those routers in a farming effort. And so that's obviously a pretty big deal. So anybody that was using the TP link browsers, I think some Linksys routers were involved as well, were potentially vulnerable to this. And it sounded like from what I read that it was a known issue, but it had not been resolved by the vendor. And so like I said, 300,000 or so routers were compromised. Other companies and softwares have reported being affected by cross-site request forgery vulnerabilities. And there's stuff that we all probably use on a regular basis. I think generally speaking, they get addressed once they've been identified. But companies like PayPal, YouTube, GoDaddy, HP Inc., the New York Times, all of these different companies have been affected by cross-site XSRF, cross-site request forgery. all these sites have been, or all these companies have actually been affected by cross-site request forgery vulnerabilities. So they crop up and frankly, it's really just due to poor programming practices. If programming if secure programming is a focus, these things become less of an issue. And obviously, some really bad things can occur. Some really malicious activities can be carried out by using this particular vulnerability attack vector. And so it makes sense that if we're talking about the potential issues that can come about from cross-site request forgery, it probably makes sense to talk about how to defend against it, particularly in the context of how you can help application developers, programmers, that sort of thing, understand what the issue is, and then how at least OWASP and some other security-minded folks have come up with recommendations in terms of how to defend against cross-site request forgery. Things like one-time tokens, which we'll talk about in just a moment. Same origin check is another one. Double submitting cookies is another one. And then if you don't mind being or lacking transparency to the user, you could use Captcha or reauthentication or other ways. But we'll talk about a couple of these in a little more detail. Particularly, one-time token seems to be the most prevalent way that cross-site request forgery is addressed. And the idea is that whenever a user authenticates to a web application, their session cookie gets set. But along with that session cookie, an additional token is created. Now, this requires that session management be maintained on the server side as well as the client side. But the additional token is created, which is tracked by the server side, and then it's also included in the cookie or in a query parameter or in some way from the client side. And then after that authentication process has finished, whenever any subsequent request is made, that one-time session token is compared to the server-side value to make sure the tokens match. So if the token submitted by the client it matches what the server thinks the token should be, then the request is approved and it's carried out, conducted, all that. If the tokens don't match, then the request is denied. And the reason this is effective is because even though attackers can craft forms and JavaScript and that sort of thing to exploit cross-site request forgery, they can't actually see the values that are set in the cookie. So if you have a one-time token specified in the cookie, the attackers can't necessarily see that. Now they can make a request and the cookie will be sent along with that request. But when they're crafting their malicious page or their malicious form submission or whatever, even if it's a post, even if it's using JavaScript, it's a lot more difficult. And so it works because they don't know what the one-time token is, and it will change every time you authenticate and that sort of thing. So this is one way, and it seems to be, just in all of my reading, it seems to be the most prevalent deterrence mechanism or mitigation strategy for cross-site request forgery. Another one that's that seems to be pretty prevalent, and what you'll see a lot is both of these two checks or these two mitigation strategies sort of paired together. But same origin check is a really simple idea in the sense that you're going to verify using the headers in the request that the source origin matches the target origin. And typically an origin is defined as a URI, a host, and a port. And the reason that this works is because certain request headers can only be accessed and written to and subsequently spoofed by the browser. So comparing the source origin with the target origin can help verify that the request is authentic, essentially is the train of thought there. But like I said, oftentimes you'll see same origin check and the one-time or synchronization tokens used together. Another sort of prevalent thing that I feel like you see, or just I see in my everyday comings and goings on the web is user interaction based stuff. So if you're as a web application or as a developer, in terms of you're defining your user experience with your code, if you don't mind sort of displaying an extra step for the user to have to sort of deal with when they're trying to carry out some sort of process using your web application, you can have them intervene. So, Captcha is one way, right, where you show something, whether it's a math problem or an image with text in it that the user has to type in, or you can actually just have the user re-authenticate. So what's your username and password, or however you perform authentication before you're allowed to, for example, transfer money. Then we're going to either ask you to put something in a CAPTCHA so we know that you're a human and you're not a script that's running trying to exploit a particular vulnerability, or we'll ask you to re-authenticate, and then almost certainly we know that it's who you say you are, and so that the request is authentic. So those are sort of the common mitigation strategies, if you will, that you'll see with respect to cross-site request forgery. There's actually some recommendations put forward by OWASP in terms of as a user, I would suspect most users don't know whether or not the applications they're dealing with on the web are susceptible to cross-site request forgery. But in the spirit of just playing safe and defense in depth and that sort of thing, and good policies at home or when you're browsing the internet, OWASP recommends that when you're done using a web application that you log off. And so that doesn't just mean close the tab in your browser. That means click the log off button that's generally provided by the web application that you're using. Don't allow your browser to save username and passwords or remember your login. We all like to do that because it's really convenient, but the trade-off there is some element of security. I know people that will use different browsers for different purposes. So if you have one browser open and you're doing your banking and you're also interested in surfing the web just sort of in a generic sense, and you're not really purposed, and you might end up somewhere where you didn't mean to end up, or you could end up somewhere nefarious, then using a separate browser to do that sort of thing could potentially stem any issues that you might run into. And then there's plugins like NoScript plugins that prevent JavaScript from automatically submitting forms when it's loaded. So that basically would force the attacker to require the user to intervene directly rather than just opening a page or loading an HTML-based email or something like that. The user would actually have to submit something manually in order to allow the attack to go through to its full extent. So those are other options as well. In terms of SQL injection, this piece of code was provided, and the question is, we have this piece of code and a static code scanner. It flagged it, said it's vulnerable to SQL injection, and the question is why, and why does it matter, and how might we fix it? So we're getting a parameter called ID from our request, and then what we do, we manipulate ID a little bit, we replace it with some values, and that's fine. But then what we do is we take largely, and it could even be unaffected by this piece of code right here, we put directly whatever the user typed is getting appended directly to our SQL query. And then we're executing that SQL query on our system, and the application goes on from there. But really where we get into trouble are these two lines right here, where we're directly taking whatever was the parameter that was passed in the request, and we're appending it immediately on the end of our SQL statement, which is not necessarily a good thing. In fact, it's a bad thing. The code's susceptible to, is susceptible to SQL injection because it doesn't perform any input validation. So, like I said, it's going to take whatever the user or the browser whatever's posted in the request or submitted in the request in the ID parameter. It's going to concatenate it with a SQL statement, and that's just going to get sent directly to the DBMS, to the database. And so you could probably think of some ways that you could get creative with crafting SQL statements to make the database management system execute a query that is potentially malicious, or at the very minimum not what it was designed to do. And so a better solution in this scenario would be to use a stored procedures. They're not difficult to build, and they have a large element of security built into them, which is nice, particularly with respect to data types and that sort of thing. So if you can't use stored procedures to make sure that if you're expecting ID to be an integer and that only an integer is sent, what you could do is you could just interrogate the parameter itself. So make sure that it's an integer, for instance. In this particular example, most likely ID is supposed to be an integer, or we'll assume it is just for the sake of discussion. You could do something very simple like trying to cast or parse that string, that ID string, as an integer and see if it passes or fails. If it fails, then you know that what you got wasn't just a number, it was something else, right? So there's things that you could do to basically validate the input, to make sure that the input is what you expect it to be before you actually append it to the SQL statement and submit it to the DBMS. You could also take a whitelisting approach to in terms of what characters you may allow. So if you're expecting an ID to be an integer, then anything that you could use regular expressions, for instance, to make sure that anything that's comprising that string, that ID parameter, is in fact a number and not something else. So that's also another approach that you could take. Just as a for example, so I don't know what the name of the web app was, but some webapp.com, you have some parameter 1, and then you have the ID parameter. And so if I were trying to exploit this for some sort of SQL injection purposes, I might put ID equals 1, put a semicolon, which would terminate that SQL statement. If you recall, the SQL statement is select star from listings where ID equals. We would see 1, and then we would have a semicolon, which is a statement delimiter in SQL. And then we could do something like drop table, some table. And maybe we don't know what this is, but maybe we do, or maybe we can figure it out. And it doesn't necessarily have to be drop a table. It could be any sort of thing. If this particular query is doing authentication and you're just looking to get a true false value back, you could do some things creatively with crafting SQL statements after the semicolon to basically ensure that you always get, or not even after a semicolon, you could add an or, an and, or some other parameters in the SQL query to make sure that you always get a true response, or a count greater than 1, or whatever it is that you're trying to accomplish. So this is just a very trivial, simple example of how you might exploit it. If stored procedures are used, the ID parameter could be specified as an integer, for instance, in which case the ID parameter, the entirety of it is equals 1 semicolon drop table some table. If you submitted this as a value in a stored procedure that was expecting an integer, this would obviously fail, and so the SQL would never get executed. With the whitelist approach, like I said, regular expressions can be used. We're expecting this value of ID to be 0 through 9, and only those numbers, or any combination of those numbers. So as soon as we see a semicolon or a drop or any other alpha or symbol characters, then we know that, or the application should know that we've gotten bad input, and we don't want to actually submit that to our DBMS and have it be processed. Some people will try to take a blacklist approach, and so people will try to just drop a semicolon on it and then write some other statement. Well, so we'll just blacklist the semicolon. If we see a semicolon, then we know that it's not going to work out, right? So, or we know that someone's trying to do something we don't intend for them to do. However, blacklisting is not necessarily a good approach because inevitably you can't think of all possible combinations. Or you can't necessarily outthink everybody else. So the whitelist approach, if you're going to go that way, is a much better approach than the blacklist approach. Attackers are creative. Oftentimes they think outside the box, and inevitably they'll find a way to circumvent that. So there you go. So a brief introduction on cross-site request forgery, a little small example on SQL injection and why it matters. And these are two sort of the most prevalent vulnerabilities out there on the web. And in terms of application code, they're things that vulnerability scanners check for significantly and pick up a lot, at least in my professional experience. So hopefully this answered some questions and gave you a better idea about these two types of vulnerabilities. OWASP is a great resource. A lot of this I pulled from OWASP. You can actually go there and learn a lot more about both of these.